In this section, we introduce a new technique for solving differential equations, and I think it's probably easiest if I start with an example to explain how it works, and then do a couple more examples. So let's start with y double prime plus y equals tangent of x. Now from this, we always go and get the auxiliary equation. So in this case, m squared plus 1 equals 0. And then you have m equals plus and minus I. Well, these both tell us that the complementary function is c1 cosine of x plus c2 sine of x. Now, the way this game works is if we throw in constants in front of cosine or sine, plug them into here, they'll turn out to be 0. So instead, we're going to try to find a couple of functions. We're going to let our particular function be u1 y1 plus u2 y2. And in that case, our u1, we don't know what it is, but our y1 here is cosine of x. Our u2, we don't know what it is, but our y2 is sine of x. Now, as you always do, when you come up with a particular solution you want to try, you plug it back into the differential equation itself. So let's go ahead and do that. I'll need to take the second derivative. So let me start with the first derivative. So I have y sub p prime, that will equal u1 prime cosine of x minus u1 sine of x plus u2 prime sine of x plus u2 cosine of x. As usual, to make life easier on myself and you as well, I am going to gather up the cosines and the sines. So I have u1 prime for the cosine plus u2 times cosine of x plus, and then I have negative u1 plus u2 prime times sine of x. Let's go ahead and take the next derivative. So then I'll use product rules on each part of these parts, and I'll get u1 double prime plus u2 prime times cosine of x minus, now I leave this part alone, u1 prime plus u2 times sine of x. So I'll get, take the derivative of this, negative u1 prime plus u2 double prime times sine of x, and then I'll have cosine of x, but I'll leave this stuff alone. And let's gather everything up then. So it looks like I am going to have u1 double prime plus 2u1 or u2 prime minus u1, all that's attached to cosine of x. And then I think I'm going to go plus negative u1 prime. I'll have negative 2u1 prime. And then I'll have negative u2, but I'll have plus u2 double prime. All that times sine of x. Once again, always scan for some symmetry here. So if I got u1 double prime, I should have a u2 double prime. If I've got minus u1, I need minus u2. Well, it doesn't have to be minus, but if I see a u1, I need to see a u2. If I see a 2u2 prime, I need to see a 2u1 prime, and I see all of that stuff. Now, the original equation we're trying to solve looks like this. Y double prime plus y equal tangent of x. So we put little p's on these things. And let me go ahead, here's my y double prime. Let me copy it and paste it in. And in addition to that, I've got to add the y itself, which was u1 cosine of x plus u2 sine of x. And I might be able to do some simplifying. If you see the u1 here, we'll cancel with the negative u1 there. And it looks like I'm left with u1 double prime plus 2u sub 2 prime. That's times cosine of x. Plus, over here, the u2's cancel. And we get negative 2u1 prime plus u2 double prime times sine of x. There's a little bit more that I'm going to do here. I'm going to release some stuff and multiply this out. What I'm going to do is rewrite this here as u1 double prime plus u2 prime times cosine of x plus negative u1 prime plus u2 double prime times sine of x. But then I released one u2 prime here, so I have plus u2 prime cosine of x minus u1 prime sine of x. Now I'm going to do a little extra piece. I'm going to get the u1s separated from the u2s and all that. So on one line I'll do u1 double prime cosine of x, and then I'll grab negative u1 prime sine of x. I'm going to do the same thing with the u2s that are attached to the other pieces. Then I'll have plus u2 prime cosine of x plus u2 double prime sine of x plus u2 prime cosine of x minus u1 prime sine of x. Now, notice this piece right here. This can be imagined as the derivative of u1 prime cosine of x. If you look, when I apply the product rule to this stuff, I'll get u1 double prime cosine of x, but then I'll take the derivative of cosine, I'll get negative u1 prime sine of x. Similarly, this piece over here can be imagined as exactly the same thing. There I'll get u2 prime sine of x, and I'll just make sure that works out. I have u2 double prime sine of x plus u2 prime cosine of x, and then plus this extra piece. Now let me go ahead and combine this stuff. So you get u1 prime cosine of x plus u2 prime sine of x. And then I got this stuff plus u2 prime cosine of x minus u1 prime sine of x. And remember, all this stuff was supposed to turn out to be equal to tangent of x. Now, if you'll recall, cosine and sine were linearly independent solutions. That means that if they're involved in systems of equations, we can solve them. What I mean by that is the following. I am going to want this piece right here to equal 0. And this piece right here, I'll want to equal tangent of x. That way I'll get 0 plus tangent of x will equal tangent of x. So there's two equations that I want. u1 prime cosine of x plus u2 prime sine of x. Set that equal to 0, and the other one will give me the tangent x that I'm looking for. I'm going to put the u1 together, so I'll have negative u1 prime sine of x plus u2 prime cosine of x, and that's equal to tangent of x. Now, to figure out what u1 and u2 are, we use Cramer's rule. I'll do a little review of that after this is all said and done. But it gives us a way of figuring out u1 prime. u1 prime will equal, these are determinants now. Treat cosine and sine and all these as like coefficients in a system of equations. So if you want to solve for this particular column of u1 primes, you replace it with the result column. But for the u2s, you put its coefficients. And we divide the whole thing by the system of coefficients. So like cosine of x, sine of x. And I'll have negative sine of x, cosine of x. You may notice this guy down here. Remember, our y1 was cosine, our y2 was sine. This down here is y1 prime, and this down here is y2 prime. This guy down here is the Wronskian. And we know it's not going to be 0 because we've talked about this before. These are linearly independent solutions. In fact, it's better than 0. Check this out. If I do and multiply across, cosine times cosine is cosine squared, and then you subtract this diagonal, so minus negative sine squared, you're going to get cosine squared plus sine squared. That's 1. Over here, 0 times cosine of x is 0, but then I'll have tangent of x times sine of x. Now, on the other hand, I can do u2 prime will equal, this time I will want this column of coefficients, cosine of x, negative sine of x, but then I'll replace this column of coefficients with the result column. 0 tangent of x, and we already know I divide by exactly the same thing. So this will give me cosine of x times tangent of x. And you'll be able to wipe out the cosine in the denominator and simply get sine of x. And over here, take out the 1 tangent of x times sine of x. So here's my 2. There's my u1 will be solved by taking the integral here. u2 will be solved by taking the integral here. Remember, you're trying to get a particular solution, so you don't have to worry about any constants. So u1 will be the integral of tangent of x times sine of x dx. It's probably easiest to rewrite this as, and I made a mistake here, by the way. When you do the diagonal across, you multiply here, but then you do the negative of this diagonal, and I didn't do the negative. So there it is. Let me put the negative here, and when you multiply this all out, you're going to get negative sine squared of x all over cosine of x dx. Now, you can't do any u du kind of a thing here because the problem is this has a higher power than the denominator. You're going to have to work an identity or two. Everybody knows sine squared of x is 1 minus cosine squared of x all over cosine of x dx. If I break this fraction up, I'll get secant of x minus cosine of x dx. And I guess I'll multiply the negative through. So negative, the integral of negative secant of x will be negative ln absolute secant of x plus tangent of x. And then I'll have plus the integral of cosine of x, so I'll have plus sine of x. So there's my u1. The u2 prime was easy. That was just sine of x. And its integral will be negative cosine of x. Like I say, you don't need any c's because we're just forming a particular solution. And that's u2, not u2 prime. So then our solution, or our y sub p, was supposed to be u1, y1, plus u2, y2. u1, well, we have all this stuff up here. Negative ln secant x plus tangent of x plus sine of x. All of that times cosine of x. And then u2 was simply negative cosine of x times sine of x with y2. So nicely, the sine of x, cosine of x cancels, and we're left with just negative ln secant of x plus tangent of x. And remember, this is just y sub p. Y, the solution, will be the y particular, y sub p plus y sub c. So y will equal negative ln secant of x plus tangent of x plus y sub c, c1 cosine of x plus c2 sine of x. So this method is making use of solutions to the homogeneous equation. Let me go back a little bit and show you why this works. It all happens because over here, since our functions cosine of x and sine of x are linearly independent, we know that the Wronskian is not 0, in this case 1. Well, that's the determinant. If the determinant is not equal to 0, then the system of equations automatically has a solution for u1 prime and u2 prime. So that's why it all works. So the trick was setting u1 prime cosine of x plus u2 prime sine of x equal to 0. That was the stuff that was inside of the derivative. And then this part, negative u1 prime sine of x plus u2 prime cosine of x. And that was equal to tangent of x. That was the trick that made it all work. Well, let's look at our functions once again. If you allow, if y sub c was instead called c1y1 and c2y2, what we have here is cosine, and then we have its derivative. We have here sine, and then we have its derivative. So if we are looking for a general way of doing this, where y1 and y2 are linearly independent solutions, then this is equivalent to u1 prime y1 plus u2 prime y2 equal to 0, and then u1 prime y1 prime plus u2 prime y2 prime equals some sort of a function. I don't think I'll use f. I'll use whatever function was in the end there. We'll call it g of x. So that was the trick. In fact, this is the trick for solving this type of equation. Y double prime plus, and we might have in here a function attached to y prime, and then we may have another function equal to gx, say. So this is the trick right here. We assume a solution, use yc in there to help us create a solution. And notice, we're not putting constants in front of y1 and y2 because that would just zero out when you plugged them into the differential equation. The fact is, we're putting, instead of a c1, we're putting a u1. This c and this c, these are called the parameters. And we're changing the parameter, or varying them, if you want to call it that. Now we're using variable parameters instead of constant parameters. So this is the game plan. And it gets pretty easy after the first example. I do want to remind you of Cramer's rule. So if you're trying to solve a system like this, ax plus by equals some solution, and then you're trying to do cx plus dy equals maybe another solution, then the way you get x is you have to think about this as columns of coefficients a, c, b, d. And in fact, before I do anything else, you're going to divide by the determinant of a, c, b, d. On the top, you'll put the bd, but since you're solving for x, you're going to replace the ac with s1 and s2. Y, in this case, will be the same kind of a thing, except you replace its column with s1 and s2, but you also divide by the same determinant. And if you recall, to do all of these determinants, you multiply diagonally, s1 times d, but then you do minus b times s2. So there's Cramer's rule that will help you solve these systems of equations that we come up with. My next example. Y double prime minus 9y equals 9x e to the negative 3x. The auxiliary equation is m squared minus 9 equals 0, so m equals plus and minus 3, which tells us that y sub c is c1 e to the 3x plus c2 e to the negative 3x. So e to the 3x is like my y1 and e to the negative 3x is like my y2. My particular solution that I'm going to form will be like this. u1 e to the 3x, this is u1 y1, plus u2 e to the negative 3x. So u1 y1 plus u2 y2. And then the conditions we want is u1 prime times y1 plus u2 prime times y2. That one was equal to 0. And the next thing we wanted to do is we wanted to do u1 prime times y1 prime. So we will have 3 u1 prime e to the 3x. But over here we'll have negative 3 u2 prime e to the negative 3x. And that needs to equal the result, 9x e to the negative 3x. So this will allow me to solve for u prime. Now you'll find it so much easier in these problems if you divide, well, I can't actually, I was going to divide everything by e to the 3x, but these are negative 3x's, so no, I'm not going to be able to get rid of it. So what we're going to do then is let's go ahead and solve these using Cramer's rule. So let's see what we have attached to u1 prime. I have e to the 3x. I want to replace the first column with the results. So we have 0, 9x e to the negative 3x, but leave the second column alone. So we have e to the negative 3x, negative 3e to the negative 3x, and all of that is over the Wronskian, which will simply be the coefficients of the whole system of equations. E to the 3x, e to the negative 3x. Down here I'll get 3e. Down here I'll get negative 3e to the negative 3x. And you know this. This is the Wronskian. You'll know that you'll have your first row, but the second row will be the derivatives of the first row. And let's go ahead and see what this equals. When I go this diagonal, I get 0, but then I have to do minus this diagonal. So I'll get minus 9x e to the negative 6x. You got to remember to add these exponents. This is all divided by, down here, I'll get negative 3, because this will be e to the 3x times e to the negative 3x will be e to the 0, so I'll get negative 3. Then I'll have to minus another 3. So here the exponents cancel themselves out. And it looks like we have 9x x e to the negative 6x over 6, or a small amount of simplifying, 3/2 x e to the negative 6x. So u1 is going to be the integral of that, x e to the negative 6x dx. You're going to need to use integration by parts. I'm not going to reuse the u, so I'll go with v and w. So I'll let v be my x, and then dv will be dx. dw will be e to the negative 6x dx. And then w will be negative 1/6 e to the negative 6x. Alright, so when I do integration by parts, I take this times this. Don't forget there's a 3/2 in front of that. So it'll be 3/2 times x times negative 1/6. I'll get negative 1/6 x e to the negative 6x. Then you do the subtraction of this part. So that'll be plus 1/6 the integral e to the negative 6x dx. And let's go ahead and simplify and all that stuff. I had 3/2 times negative 1/6 x e to the negative 6x. Here will end up being negative 1 over 36 e to the negative 6x. I can factor out an e to the negative 6x from everything. I'll get 3/2 times negative 1/6 x minus 1 over 36 times e to the negative 6x. And let me multiply it through. If I multiply it to this, I'll get negative 3 over 12, which will be negative 1/4 x. And then in this part here, I'll have 3 over 72 will be 1 over 24. Then for my u2 prime, this time when I form my solutions, I want to use the first column as it is. So my first column will be e to the 3x, then 3e to the 3x. But the second column, I'm going to go and replace it with the result, which was 0, 9x e to the negative 3x. You'll notice I've already evaluated the Wronskian from the first part. That gave me a negative 6 down here. So I'll just put over negative 6. And then let's go ahead and multiply it through. When you do this diagonal here, notice the e's cancel out and you're left with just 9x, or negative 3/2 x. And then so u2 will be the integral of that, will equal negative 3/4 x. Now we're ready to do our particular solution, which is y1, or u1 y1 plus u2 y2. u1, where did it go? There it is. Negative 1/4 x minus 1 over 24 e to the negative 6x. y1 was e to the 3x. On the other part then, we have minus 3/4 x e to the negative 3x. That was y2. And I can simplify a little bit. If I want my total solution written out, when I have this part here, I'll have e to the negative 3x for that part too. So I can just do one big fat e to the negative 3x, and then just collect everything else inside. So it looks like I made a mistake there and there. Let me go ahead and now put it in order. Negative 1 over 24 minus 1/4 x minus 3/4 x squared. And there is your solution. Oops, that's y sub p. Let's try this again. These solutions look rather long, and they are, but we've tackled them in parts. For my last example, these are rather heavy, so I'm not doing a lot of examples. 4y double prime minus 4y prime plus y equals e to the x over 2 times the square root of 1 minus x squared. So once again, let's go to the auxiliary equation. This factors quite easily. 2m minus 1 squared equals 0. And we see that m equals 1/2, but it's repeated. So our complementary function is c1 e to the x over 2 plus c2x e to the x over 2. Recall you do that when you have repeats. So with my complementary function, I need to form my solution, but not yet. What I need to do first is to take and divide the whole thing by the leading coefficient. So I'm going to divide by 4. Now I'm ready to form my solution. Y sub p will equal u1, and my y1 was e to the x over 2. My u2, my y2 was x e to the x over 2. And then what we need to happen is I need u1 prime e to the x over 2 plus u2 prime x e to the x over 2 to equal 0. Remember, this is u1 prime times y1 plus u2 prime times y2. Then the next line is u1 prime, and now I take the derivative of y1, and I'll end up with 1/2 e to the x over 2 plus u2 prime. For this stuff in here, I'm going to have to use a product rule. So the derivative of x is 1, so I get e to the x over 2 plus 1/2 x e to the x over 2. Now over here, this was supposed to equal the result 1/4 e to the x over 2 times the square root of 1 minus x squared. Now you may notice that there is an e to the x over 2 attached to absolutely everything. So I'm going to divide everything by e to the x over 2. It's not 0, so this is okay to do. If you go strictly according to the script, you'll go right to solving for u1 prime and u2 prime using matrices, and the e to the x over 2 will cancel out anyways. I just choose to do it now to make my life a teeny bit easier. Once I do that, I have u1 prime plus u2 prime x, that's equal to 0. And then I have 1/2 u1 prime plus u2 prime times 1 plus x over 2. And that's supposed to equal 1/4 times the square root of 1 minus x squared. And now let's go to the solutions. u1 prime will equal, don't put 0 and 1, or 1 and 1/2 for the first column, put the result column. So I have 0, 1/4 times the square root of 1 minus x squared. And then here I'll have x, 1 plus x over 2. And the denominator goes the Wronskian. 1x, 1/2, 1 plus x over 2. Now whatever I get for this, I'll copy it for the next part that I do anyways. When I multiply through here, I get 0, but then I get negative 1/4 x times the square root of 1 minus x squared, all over what we have down here. When I do this, I get 1 plus x over 2, and voila, minus 1 minus x over 2, I get a 1. That's easy enough. So u1 will be the integral of that stuff And this is an easy u substitution. Or in my case, I'm not going to use u, I'll use w. W equals 1 minus x squared. dw will be negative 2x dx. Or better yet, negative 1/2 dw equals dx. So I'm going to have negative 1/4 times negative 1/2. I'll have 1/8. The integral w to the 1/2 dw. That will equal 1/8 times 2/3 w to the 3/2. A little simplifying here. I get 1/12. The w is 1 minus x squared. And then my u2 prime was equal to almost the same thing. This time I'm going to replace, let's see if I can find it here. Oh, I went way too far up. This time I'm going to replace the second column with the result column. So I'll have 1/1/2. Remember, we divide this whole thing by 1. So 1/1/2. And the other side was 0 1/4. We already did the Wronskian in the last problem, so I'll put a 1 there. So I'll just get 1/4 times the square root of 1 minus x squared. Well, u2 will be the integral of that. Probably the easiest way to do this is with a trig substitution. I don't happen to know the formula off the top of my head. So it might be best to allow sine of theta to equal 1, not 1 minus x squared, to equal x. Then cosine of theta d theta will be dx. So what do we have here? I have 1/4, the integral. Now instead of 1 minus x squared, you're going to have 1 minus sine squared of theta. Instead of dx, you're going to have cosine theta d theta. Now this 1 minus sine squared is cosine of theta, cosine squared of theta. When you take the square root, you technically get the absolute value of cosine, but we don't know where we're integrating on, so I'm just going to stick with the positive version of that. And I'll end up with cosine squared of theta d theta. And to integrate this properly, you probably remember that you're supposed to use the identity, the half angle identity, or maybe it's the double angle identity. I think it's a half angle identity. Like so. Let me go ahead and pull the 1/2 out. And that will be 1/8 theta plus 1/2 sine of 2 theta. And now I'm ready to put my theta back. If you recall, sine of theta was equal to x, so theta equals arc sine of x. So I get 1/8 arc sine of x. Now for this part here, I'm going to let you recall that sine of 2 theta is equal to 2 sine of theta times cosine of theta. That way those two cancel. Sine of theta we already know is equal to x. Cosine of theta, if you do this little game, you probably have seen it before. This is a right triangle. Sine of theta was equal to x, and sine of theta is opposite over hypotenuse. So you can do an x here and a 1 here. Well, that will tell you that the other side is the square root of 1 minus x squared. Or you just know the cosine of theta is the square root of 1 minus sine squared, and you'll get this. So there's my u2. So y sub p will be u1 y1 plus u2 y2. That equals, where is my u1 at? See if we can find it. 1/12 1 minus x squared. y1 times e to the x over 2 plus u2 is 1/8 arc sine of x plus x square root of 1 minus x squared. All that is times x e to the x over 2 to the 3/2. And I'll go back and fix this in case I refer to the notes later on. So I forgot the 3/2 that was attached to that. So anyways, my y will equal all of this stuff. I'll try to write it even smaller. You know, you've got an e to the x over 2 attached to each thing. So I'm going to have an e to the x over 2 times 1/12 1 minus x squared to the 3/2 plus 1/8 x times arc sine of x plus x square root of 1 minus x squared plus c1 e to the x over 2 plus c2x e to the x over 2. That is a big solution.